out the magnetic field that would be produced by a little tiny current loop lying at the origin parallel to the xy plane. And what we discovered was that it had exactly the same magnetic field we would have gotten from a magnetic dipole, which had a magnitude, the current times the area of the little loop, and a direction perpendicular to the loop, so that if you curled your fingers in the direction the current was flowing, your thumb would point in the direction of the dipole. In other words, if we had this situation, here's the xy plane, z-axis out of the board, and we had a little current loop flowing like that, great. So that this was a current I, and the area was A. Then, if you assign to that a magnetic dipole given by IA z hat, so that you curled your fingers in the direction the current was flowing, your thumb would point this way, which is the z direction. That the magnetic field this little current loop would produce was given by exactly what we had when we calculated it for a dipole, namely k over r cubed times 3 m dot r hat minus m. So now we know the connection between current loops and magnetic dipoles. And we can always solve the problem either way. We can solve it just integrating the Biot-Savart law to get B, or we can break the circuit into little magnetic dipoles and add up the contributions from each dipole. That was the analog of Coulomb's law. It was the statement that B at R was K sub m times the integral over the volume of J of R prime cross R minus R prime over R minus R prime cubed. It was the magnetic analog of Coulomb's law, which looked almost the same. K electric integral d cubed R prime. Here we just had a charge density times R minus R prime over R minus R prime cubed. There's the only change is you replace charge density by current and you get a cross product. And we can always solve it with this, or we can solve it with that. Okay? Now, let's take a look at what the fields will look like then from a given current arrangement. Now, I take a magnet, I put it in here. Now that is a dipole. Now what do we expect the field lines to look like? They ought to come out of one end of the dipole. They got to be closed loops. They got to come out here, they got to come in here. So they got to make some sort of a path like this. Now, we can visualize that by putting down little magnetic needles. We take little compasses. These are iron filings. So they're elongated pieces of iron, which will become magnetized and will point in the direction parallel to the magnetic field. Because we've already seen that the primary effect of dipoles is to line up with one another, or of a dipole to line up with the magnetic, magnetic field that's present. So, put a little bit more on here. And now you can see the field lines run like this, and they, of course, are three-dimensional because the dipole is cylindrical. Now, let's start putting in some combinations of dipoles. Now, suppose I do this. Now, field lines can come out here, go in there, come out there, go in there. So, now what I get is field lines running this way and that way. On the other hand, if I reverse this, now I couldn't get any field lines going from there to there. So now, what I simply get is field lines running out here and in there. Making sense to everybody? So it's exactly what we would expect the things to look like. All right, now over here, no, I think I'll save this one for a little bit. When we did Coulomb's law for electrostatics, there were three ways to solve electrostatic problems. We could do it directly from that, which worked if we knew the charge distribution. So we could solve it directly from this one if we knew the current distribution. We could do symmetry. We could use Gauss's law. If we had a nice symmetry, then we were able to use Gauss's law to solve a very small number, but interesting number, of electrostatics problems. We suspect there is a law like that for magnetism, and we're going to get that next. The third possibility was to get the differential equations that described E. Namely, the divergence of E was 4 pi k rho, and the curl of E was equal to 0. Well, we should be able to do the same here. Get the differential equations that describe B. Now, we can kind of guess what they're going to be. We know from our discussion of electricity that if we specified the divergence and the curl, this gave us the production of lines which begin and end. This gave us the production of lines that were closed loops. And if you specified both of those, you would have completely described the field. So we think we probably want to do the same thing for magnetism. Now, can we guess what those are going to be like? In magnetism, are there any lines that begin and end? No. They're from dipoles. They come out of one end. They go into the other. So we expect we're going to get the divergence of B equal to 0. Now we'll check that in a minute and see that that's really what happens. On the other hand, so we're guessing the divergence of B will be equal to 0. But if that's true, that had better not be equal to 0 or we wouldn't get any lines. Because if they neither begin nor end or are closed loops, there aren't any. So we suspect the curl of B is not going to be equal to 0. Okay? Now, what do we expect that it should be? Well, let's see. Let's look at a situation that we can easily calculate. Suppose we had a very long straight current. Okay? Now, what must the field lines look like for that if they're going to be closed loops and have a cylindrical symmetry? What are the possibilities for a cylindrical symmetry? Lines that go radially outward or lines that are circles. Right? So viewed from the end, the two possibilities are this. This is a side view, and this is an end view. The other possibilities are that, right? Now, this is what we had for electricity. Those lines begin and end. This is what we better get for magnetism. Now, that being the case, B will be a constant everywhere around one of these loops. And so, if we were to calculate the line integral of B dot dl around this loop, we would get B at this position times the distance around, which is 2 pi r. So this should come out to be B times 2 pi r. Okay? But now, if we calculate that, we know from Stokes' theorem that the line integral around the loop is the same as the integral of the curl over the area. So this should be the integral of the curl of B dot dA over a cap placed over this thing. Okay? So, if we calculate B, then we ought to get an idea of what the curl should come out to be. Making sense? Okay. So, let's see if we can calculate B for our long straight wire. Well, we'll go to our picture here, and let's calculate B at some point up here. And it'll be a result of, from this thing, the magnetic fields produced by little chunks of current lying along this axis. So let's make this the z direction. Okay, so now that integral for B will become k sub m. And now this times this will be replaced by IDL. As we said, it has to be, take account of the geometry. In this case, it's along a line. So a current times a current density times a volume becomes a current times a length. And so you have I dl, but that is simply dz in the z direction crossed into r minus r prime. Now r is, so r minus r prime over r minus r prime cubed. And then you're going to integrate z from minus infinity to infinity. So let's go out here at some position. Let's just make this, it's obviously going to have a cylindrical symmetry to it. Let's just calculate it at one position up here. And what you're going to have, you're going to take r to be x, x hat, y, y hat, z, z hat, r prime, and let's calculate it. Since it's the same everywhere along this wire because it's infinitely long, we'll calculate it at z equals 0. So we'll just have that. And r prime, there's no x component, no y component. It is z, z hat. And so r minus r prime is x in the x direction, y in the y direction, and minus z in the z direction. And so the magnitude, r minus r prime cubed, is x squared plus y squared plus z squared to the 3/2. Now, I dz z hat crossed into r minus r prime, x hat, y hat, minus z hat. Z hat cross x hat. Z cross x is y. So you get I dz times x y hat. And then we got z cross y. Z cross y is minus x. So it is minus y x hat. And z cross z is 0. Okay? So now we have everything we need to calculate this thing. And we get b of x, y, z is equal to k sub m I times the integral of x y hat minus y x hat dz divided by x squared, y squared, z squared to the 3/2. Okay with everybody? Yes?
From our drawings, what are we considering to be r prime?
R prime is the vector from our origin to where the little current is located. So in our case, it's just along the z direction, a distance c from the origin. Okay, so now let's calculate this at a point up here. Say x is this way, y is out of the board, and that's c. So let's calculate it at the point x, 0, 0. So b of x, 0, 0 is k sub m I times the integral of x y hat. So we just take the y hat outside. So we have x, that's just a constant. That comes outside. And we're left with dz over x squared plus y squared plus c squared to the 3/2. From minus infinity to infinity. Okay? So all we have to do is evaluate this integral, but that's a trivial integral to evaluate. And the result is that you'll get k sub m I, and then you get 2 pi times x squared plus y squared square root. In other words, the magnetic field at this point is k sub m that's not quite right. This is, okay, let's do it. So we've got k sub m, which is mu 0 over 4 pi times I times x. And now, the integral of that, 1 over a squared plus x squared to the 3/2. It's something like, let's check it out here, a squared plus x squared to the 1/2. Now, if you took the derivative of this, what would you get? You would get minus 1/2 times 2x a squared plus x squared to the 3/2. And so let's that's so minus x. So I need to add to that I need to add to that x over a squared plus x squared to the this is why you have a calculator, so you don't have to struggle to figure this out. Okay, so let's integrate this thing. Okay, F3. Integrate. Well, I can't make this thing do it correctly. The answer will come out to be, when you do the arithmetic, you will get mu 0 I over 2 pi x. Okay, we could work that out, but that's what you're going to get. So, what we discovered was that we had this thing, and it points in the y direction, y hat direction. So, what is the curl of B then? Well, we can just do the arithmetic on this. Take the curl, and so you'll have x hat d by dx, y hat d by dy, z hat d by dz, crossed into B. And so that is mu 0 I now, to do this, we need to have it in a general location. I can't calculate the curl just for one specific value. I've got to have it as a function of x, y, and z. And so the easier way to do this, see what I'm saying is, I can't calculate the curl by putting this in, because that's only true at one precise spot, namely the place along the x-axis. I need it as a function of x, y, and z, not evaluated at that particular location. So the easier way to do this would be to recognize that what this is really is the distance from here to here, which if I did it in cylindrical coordinates would be rho. And it is pointing in the positive y direction, which is out of the board. And that would correspond to the theta direction. Because if you've got this arrangement, this x, this y, then theta is this way, rho is that way. And so what's happening here is that this is pointing in the y direction when you're on this axis. And that means it's pointing in the theta direction in general. So that what I really have is that b of rho theta is equal to mu 0 I over 2 pi rho theta hat. Now, let me then calculate the curl in terms of cylindrical coordinates, in which case it is rho hat d by d rho plus theta hat over rho d by d theta plus z hat d by dz crossed into mu 0 I 2 pi rho theta hat. And what do we get? We get rho hat crossed into the derivative of this thing with respect to rho, and that gives us minus mu 0 I 2 pi rho squared theta hat plus derivative of theta hat with respect to rho, but that's 0, plus theta hat over rho crossed into d by d theta. Well, that isn't affected, mu 0 I 2 pi rho. And d theta was minus rho hat. Minus rho hat. Okay. And then d by dz, but that isn't affected. And rho hat cross theta hat, that's going to be a z hat. And this is going to be a z hat. And so what we're going to have, rho cross theta, that's from our picture here, rho crossed into theta, points in the z direction. So we get minus mu 0 I 2 pi rho squared in the z direction. And the second term is theta cross rho. And theta cross rho is just opposite to rho cross theta. So that is plus mu 0 I over rho squared z hat. Those cancel out, and we missed one term here. Now, what term did I miss? Yeah, I failed to do d by d theta, d by d rho of theta hat. So there's an extra term here, which is rho hat cross d theta hat d rho is minus rho hat. So that one is still 0. Let's see. B is mu 0 I over 2 pi rho theta hat. That's certainly right. So now I take the curl of B, and that's that. And so I got mu 0 I over 2 pi rho squared, that's right, minus sign, times theta hat, and rho hat cross theta hat is in fact z hat. Okay, that's right. And then I took mu 0 over 2 pi rho d theta hat d rho, which is 0. D theta hat d rho is 0, so that's okay. And then I had d by d theta of that, and that is just d theta hat d theta, which is rho minus rho. So theta hat cross minus rho, so that's that one. Z hat by rho squared. And then d by dz okay, so what I got from this was that the curl of B was equal to 0, except, okay, yeah. So in general, this thing is 0, no mistakes. But there's one place where that calculation is wrong, and that is the calculation at the point rho equals 0. Because at rho equals 0, we've got a singularity in here. Because we've got a 1 over rho, and we got a run over rho squared. And there's a singularity at that point. So we can't trust this calculation at the point rho equals 0. We can trust it everywhere else. And everywhere else, you get the curl to 0. At rho equal to 0, you can't trust that. So we expect that we're going to have something special happening at that point, and that's what we're going to investigate next. Okay, everyone understood things to here? So what we've concluded is the curl of B is 0 everywhere except here on the line. Everywhere else, the curl of B is 0. Okay, now let's proceed to calculate the divergence of curl mathematically. So first, let's do the divergence. Divergence of B. Well, this is derivatives with respect to r. That integral is with respect to r prime. So I can take the integral, the derivative inside the integral, because this is derivatives with respect to r, and that's integral with respect to r prime. Yes? The curl of B cannot be 0, but it can be 0 everywhere except where there is a current. What we've just shown is that if we're not at rho equals 0, which is where the current is, the curl is equal to 0.
Oh, okay. So current.
So what's going to happen is that the curl will be 0 everywhere except where the source current is located. Yes?
But wouldn't that imply that at your singularity it would be infinity regardless of how strong the current actually was? So you'd have like infinity
gonna
equals
get-
5, infinity equals 4.
We're going to get what's known as a delta function, which has the value infinity at 0 and 0 everywhere else, such that the integral is a finite number.
That didn't really show up very often in real life. And the total charge is not the value usually apply a lot of force. But the ammeter that around the wire is shaking around.
It's the same problem we got when we used, got the divergence theorem to get divergence of V is 4 pi k rho. Now, rho is 0 everywhere except where the charge is actually located. So you got divergence of V equals 0 everywhere in space except at that one point. And if you calculated the divergence for kq over r squared, and didn't worry about the singularity, you get 0. When you worry about the singularity, it must turn out that that result gives you a finite number because you get an electric field. Now the same thing is going to happen here. We'll work it through in detail, and it'll make sense. So let's calculate the divergence of B first. The case of M is okay. Now, we'll take the divergence inside. And so we have the divergence of J of R prime crossed into, now, R minus R prime divided by R minus R prime cubed is the same as the gradient with respect to prime of 1 over R minus R prime because, consider this, what is the gradient prime of 1 over R? Gradient of 1 over R. Well, what you're supposed to do if you do it in spherical coordinates, you'd have R hat d by dr and so on. And this thing is minus R over R squared, which is minus R divided by R cubed. Now, if you're not clear on that, how would we calculate that? It'd be R hat d by dr plus theta hat over R d by d theta plus phi hat over R sine theta d by d phi dotted into, not dotted, just applied to 1 over R. Okay, now what happens? This one gives you minus R hat over R squared. There is no theta dependence. There is no phi dependence. So you just get that, which is equal to this. So the gradient of that will be this with a minus sign because of the minus sign there. So we can write this as equal to plus R minus R prime plus the gradient of 1 over R minus R prime. So we write this gradient prime 1 over R minus R prime. Okay with everybody? Now, I could also have written this thing as the minus the gradient of this, because the gradient prime is just minus the gradient of the thing by itself. And so I could also have written that with this, with a no prime on it and a minus sign. Okay? Now, we have to calculate the del dot of the product of two vectors. So we have to calculate del dot A cross B, divergence of A cross B. Well, we know how to do that. So we have the divergence of A cross B. And remember, our procedure for doing this was to use the vector cross product. A cross B cross C was C dot A times B minus B dot A times C. And so to get what we want is we need to take something dotted. We need that dot product there. So let's take this to be del and A to be A and B to be B. Now you remember our rule was that we put the derivatives to the left of whatever they're operating on. So let's first operate on A. So this would become divergence of A times B. This one would be B would be del operating on A dot B. And this would be A cross, well, this is fine, but that's not the best way to do it. Let's do it slightly differently. Let's use the fact that you can do a cyclic permutation on the products, so that the divergence of A cross B is the same, just to a cyclic rotation of these things. So we can interchange. Could just move this one over to this side, or just interchange these. And so it becomes A dotted into del cross B. You can interchange the dot and cross in a triple product with vectors. And so since I have to apply the divergence to both of these, what I'll get is the divergence of A cross B will be equal first to A dotted into the curl of B. And now I want to apply it to B, but to do that, I'm going to reverse the order here, which will give me a minus sign. So I'll get B dotted into the curl of A. So that'll be the dot product of the divergence of the cross product of two vectors. Okay, now in our case, A is J, and this is B. Now, A is a function of R prime, and therefore derivatives of that with respect to that are 0. So this term is 0 in our case. Yes?
I was just going to ask what that J is coming from. They were saying it's the charge density?
That is the current density. It is amps per cubic meter, or square meter, I mean. Okay, so that means that what we get here is K sub m times the integral d cubed r prime of, all we got is the second part of this, which is this, j of r prime dotted into del cross b, which is grad prime 1 over r minus r prime. Okay? Now, I can change this to a del prime if I put a minus sign, because these are derivatives of r prime, that's derivatives of r, there's just a minus sign difference. Stop. Can't even make it quit. Okay. So, I write that as equal to minus k sub m times the integral d cubed r prime j of r prime times del prime cross del prime 1 over r minus r prime. But this combination, the curl of a gradient is always 0. The curl of any gradient is 0. And therefore, this term is 0. And we get the divergence of B is equal to 0, as we expected. Okay, now we need to find the curl. Are you all familiar with this, that the curl of a gradient is 0? Okay, then let's check that. So what is the curl of the gradient of anything? Well, it's x hat d by dx, y hat d by dy, z hat d by dz, crossed into, now the gradient is x hat dA dx, y hat dA dy, z hat dA dz. Okay, so the d by dx's don't change the unit vectors. And so when I take this product, I get x hat cross. D by dx of that does nothing to x hat and makes that d squared a dx squared. Okay? Now I do this one. And I get x hat crossed into, it does nothing to the y hat, dA dx dy. And now I do this one. x hat cross does nothing to the z hat, d squared a dx dz. And now I do this one. Y hat cross does nothing to x. And so you get d squared ax dx dy. Okay? And then you get y hat cross does nothing to y. And so d squared a dy squared. And then y hat cross does nothing to z. D squared a dy dz. And then you do the same thing for z. And you get z hat cross d squared a dz dx plus z cross y d squared a dz dy plus z cross z d squared a dz squared. Now x cross x is 0. Y cross y is 0. Z cross z is 0. And then look at what's left here. You have x cross y, and you have y cross x. But those are just equal and opposite. They're z and minus c. The cross products are the same. And therefore, those two terms add up to 0. And so with each of the other pairs. And so the curl of a gradient is always 0. Okay?
I tried to see if I
I'm not understanding the question.
previously we had the magnetic field due to a Galileo charge.
Yes.
I couldn't do it. I looked at it. I was like, oh, I don't know. I can't figure out why I should be able to do this. I know that
Yeah, it's
there was a bear, and I couldn't figure out. That would be easy, but there was a bear to be above the denominator.
yeah, but you can do that. It is a 1 over that square root, and then there's a term with a z over the thing to the 3 halves, something like that. I didn't want to take the time to calculate it out. You can look it up in any integral table, or you can work it out in 10 minutes, or in your case, probably 2 minutes, but in my case, 10 minutes. And we'd figure out what it was. All right, so let's look at the curl of B. Well, the only difference is going to be, as before, I can take this inside, and so I will have that. And so now I need to evaluate the curl of a cross product. And so I need to evaluate the curl of A cross B. Now, that we'll do exactly the way we did before with our, triple product. But we're going to run out of time, so I'll do that for you on Wednesday. And this is going to be much more complicated, and we're going to have to look at the delta function, which is the question you were raising. And so that'll be a good thing for next time. Okay, now you're going to turn in the exams today, so I'll just give them to David. And did they go okay with everybody? You're not willing to make such a rash statement.